So on Monday, we started our final section on discrete mathematics, looking at principles of counting, and we're going to be continuing that today, looking at some more examples of counting. So for those who watched the pre-lecture was about combinations mainly. So on Monday, we talked about the multiplication principle. So that's where you've got independent events and you have a set number of outcomes for those events, and you just multiply the number of outcomes for each of those events. For example, if you roll a dice, there are 6 outcomes. If you flip a coin, there are 2 outcomes. So the total number of outcomes of rolling a dice, then flipping a coin, is going to be 6 times by 2, which is 12. Okay. We also talked about the permutation, the way to calculate permutation. So a permutation is where you have a set of objects and you are drawing a set of objects without repetition from that list. And the order matters, okay? So if I have a set of balls in a jar and I want to take out, I'm going to label these 1, 2, 3. The order in which I take these out, say 1 first, then 3, then 2. That's a permutation. That would be a different permutation than 1, 2, 3. Okay, so we worked out how to define permutations. The pre-lecture talked about combinations. So combinations are where this time we have an unordered subset. So we don't care about the order now, unlike in permutations. Again, we don't have repetition. So example here from the pre-lecture, if you have 3 objects, call them 1, 2, 3, what are the possible combinations with just 2 of those? So 1 and 2, 1 and 3, 2 and 3. Nice and simple. There's a way that we can calculate this in general, which is related to our formula that we had for permutations. So if we want to work out the combinations where we have a list of n objects, and we're taking k of those, where k is less than or equal to n, out of that larger set, then the number of combinations is just going to be the number of permutations divided by k factorial. We can write this a little bit simpler below as something called n choose k. So this is how we say this thing in the brackets here. When we see this nk, that's read as n choose k. This is telling me the number of combinations of k objects drawn without repetition from a larger set, or larger or equal set n. This turns out to be n factorial. So we talked about factorials on Monday and how to calculate those. So it's n factorial divided by k factorial times by n minus k factorial. So this tells us the number of combinations, and it's related to the number of permutations by taking the number of permutations and dividing it by k factorial. It will work. There we go. Okay, so the reason this happens is we can imagine we have a set of objects, n objects. We choose k of those, and there are p, k, k, so the number of permutations for k of these things drawn from a list of k, there's lots of k's here going on, is k factorial, okay? So we can do this for any number k, and this leads us back to this formula up here. Sorry, there's a bit of lag going on between my pen and my tablet. We end up with this formula here relating the number of combinations, the number of permutations. Okay. Okay, so went through various examples in the pre-lecture. For example, if we have a jar containing 6 colored balls and we want to just select 4 of those, how many different combinations of colors are possible? Again, make sure you know the difference between combination and permutation. So permutation, the order matters. Combination, the order does not matter. Okay. So to work out this, we have 6 objects and we're choosing 4 of them without repetition. So that's 6 choose 4. That's what this thing here is read as, 6 choose 4. So 6 factorial over 4 factorial times by 6 minus 4 factorial, which in this case is 15. As with before, we can do various types of cancellation here to make these a little bit simpler sometimes. Okay, there are various other examples. I'm not going to go through all of these here, but we can combine things like the multiplication principle with our combinations. So that was pretty straightforward there. And if we have cases like this where we have repetition, if we care about how many different words we can have, and words used in the loosest sense here of a string of letters from Mississippi in this case. There's lots of S's, lots of I's, okay? And there's also 2 P's. So in order to work this out, we need to think about the repetition of our S's, I's, and P's, and we can label these as I1, I2, I3, I4, S1, S2, S3, S4, and P1, P2. And then to work out our actual number of different words, well, there are 11 possible letters here, and we need to divide that by the number of repetitions for the same word. The reason being, if we imagine, in this case down here, we can make lots of words of that say Mississippi with these letters by changing the S's around, changing the I's around, changing the P's around. It's still the same word though, so we want to have different words, okay? You might say, why does any of this matter? Well, we care about lots of things in genetics where we think about sequences of gene sequences. And so we might want to calculate the number of different gene sequences we can have. But if we change the T's around here, we haven't changed the gene sequence, okay? So while some of these examples might seem a bit, why do we care about how many different words we can form from Mississippi? These are used in things like bioinformatics, okay? Okay, before we go on to problems, does anyone have any questions about the pre-lecture material? Yes.
So the last example we did,
yes.
Have because it's just one factor, right?
Exactly, yes. There was only one M, so we didn't need to account for that being repeated. Good question. Any other questions? Okay, let's go through some problems. The nice thing about these problems is they're all quite short. Okay, so here we've got a bag containing 10 different candy bars, and you're allowed to choose 3 of them. So how many choices do you have? Nice, simple, straightforward question. Key piece of information, we have, turning this into a mathematical expression, we have 10 different candy bars, so we have a set of size 10. We want to choose 3, so we need a subset of size 3. So those are our key numbers here. How many choices do we have? Well, we're not asked about the ordering of this list, so it doesn't matter if you choose, say, a Snickers or Hershey's, or I don't actually know what Canadian candy bars are, so I'm going to use British ones. Snickers, Mars. Do you guys have Mars bars here? Okay. Snickers, Mars, and like a Hershey's bar or something. Okay, it doesn't matter the order in which I choose them. I still end up with the same 3 candy bars, right? Okay. I was really worried I was going to show my age then by saying one really archaic that no one's ever heard of. Okay. So what do we do here? We're caring about combinations. We don't care about the order of things here. So it's 10, choose 3. Okay, we have a set of 10 objects and we're choosing 3 from them. 10, choose 3. Note that this number here is our K, this is our N, and we need to always have K less than or equal to N. Okay, you can't end up with something like 3 choose 10, because that's saying we have 3 objects and we're choosing 10 from that list of 3. Okay? Impossible to do that without repetition. So what does that look like? Well, we write it in this form here, 10, choose 3, these long brackets. Note that this is not a fraction. This does not mean 10 over 3. This is not a matrix or a vector. 10, 3 does not equal some vector 10, 3 like this. This in this context specifically means 10, choose 3. How do we work that out? This is n factorial, so n is 10 here, divided by k factorial, k is 3, and then brackets n minus k, so 10 minus 3 factorial. So expanding this out, we can write this as 10 times by 9 times by 8 times by 7 factorial, divided by 3 times by 2 times by 1 times by 7 factorial. The reason I've written it in this form is that we can cancel those 7 factorials. They're exactly the same. You can also do a little bit more cancellation here. If you want to work it out in your head, that is. You could just plug these into a calculator. But for the purposes here, we can divide that 9 by 3 and cancel the 3 from the bottom. There's 2 here. We can take out a factor from that 8, say. So we're now left with 10 times by 3 times by 4, which is 120. So there are 120 different ways that you can choose 3 candy bars from a set of 10 counterparts. Again, this is unordered. I'll leave it as an exercise for you guys if you want to work out how many different ordered ways there are that will require permutations that we covered on Monday. Okay, let's go through another example. So here we've got 12 children. Too many children, yeah. 12 children divided into 3 groups, one of size 5, one of size 4, and one of size 3. Okay, and we want to know how many ways can this be done if the order within each group is not important. So that piece of information is telling us that we want combinations rather than permutations. If it said that the order matters, then we want permutations. So what does this look like? Well, we have a group of 5. We have a group of 4. We have a group of 3. So let's think about this first group here, this group of 5. How many different ways can we select this group of 5? This is just going to be 12, choose 5. We're starting off with 12 children, and we're choosing 5 of them to go into this first group. How about the second one? Please. That's the very good question. That's what we have to decide here. So the question is essentially, do we include those children again, or are we not including them anymore? Well, it does here. They're divided up into 3 groups. So it's implying that, and we're told that they're groups of size 5, 4, and 3. So they can't be in more than one group, 5, 4, and 3. If we add those things together, we get 12. Okay, so each child is in just one group. In that case, what are we doing here for the second group? I'm going to pick on you because you're on the right track. 7, choose 4. Perfect. And then the final one is just going to be 3, choose 3. So we've only got 3 students left. So this is just going to be 3, choose 3. Now tell me what 3, choose 3 is instantly. 1. Okay. If the order doesn't matter and you've got 3 individuals and you need to choose 3 of them, there is only one combination. It's the one that has all of them in. Okay. So how do we then work out the total number of ways that this can be done? Well, here we can combine our multiplication principle. Is that a question? Yeah.
Yeah. But then if you had the word specifically as like 12 children are divided into 2 groups of 4, 5, and 3, then would be the
No, because you're going to be multiplying these things together, they will ultimately cancel out.
Okay, so this.
Yeah. Yeah, exactly. Yeah. Okay, that's another thing you can have a go in your own time to just like work that out, put them in a different order. So rather than choosing the 5 first, do the 4 and the 3 first, and then work it out. And because you'll have these factorials there and you're multiplying these things together, you'll just get cancellations. Okay. Okay, so how many are there? There are. We just need to multiply these things together. Okay. So there are 12 choose 5 ways of choosing the first group, 7 choose 4 for the second group, and 3 choose 3 for the third group. So obviously this 3 choose 3 just cancels. If you work that out, this should be something around 22,720, I think. I did not work that out in my head. I'm trusting that what I've written down is correct. Okay, so there are 22720 ways of creating these groups. Okay, I'm going to get you guys to do the next one. Don't calculate the actual final answer unless you really want to and you've got a calculator, because it's a very large number. Okay, so here we've got HIV transmission. We have a small number of small number of genotypes are transmitted. So this happens in HIV. There are these genetic bottlenecks. Whenever there's transmission, you have lots of diversity within a host, but only a small number of a small amount of genetic variation is passed on to the next host. So you often see these genetic bottlenecks, not just with HIV, with other pathogens as well. It's particularly common in HIV though. So we can think about, given the diversity of viruses within a host, what are the different, or how many different combinations can actually be passed on to another host, okay? So have a go at turning this word problem into a problem of combinations, and then figuring out what the answer is, okay? Who wants a little bit more time? No one, okay. So let's just read through this. So once an individual is infected with HIV, a very large number of different virus genotypes arise through mutation. However, during transmission between individuals, a bottleneck occurs in which only a subset of these genotypes are passed on. Suppose we have 150 HIV genotypes present in an infected individual, but only 10 distinct genotypes are passed on during transmission. How many different possibilities are there for the pool of genotypes transmitted? Okay, so if this was given to you, like, you know, we're going to be doing combinations now because we're talking about combinations. How do we distill this set of information into a mathematical formulation? That's kind of the key skill here. So do what I do and go through and underline things or highlight things to pick out the key pieces of information. Okay, so what's the first key piece of information? We're only having a subset of things transferred. We're starting off with 150, so that's our large set. Only 10 distinct genotypes are passed on. So we've got our N and our K. Our N is going to be 150 and our K is going to be 10. We don't know yet whether it's a permutation or a combination situation, but here we're asked how many different possibilities are there for the pool of genotypes transmitted, okay? So because it's asking for a pool of genotypes, you can imagine this as being genotype A, B, C, D, and so on. There's no ordering in this pool, right? So this is not a question of permutations. We don't care if an individual gets genotype A, then genotype B, then genotype C, and so on, or C, then B, then D, and so on. It's just a pool of genotypes, so it's an unordered problem. That means we need to use combinations, so we need to use N choose K. So what is the phrase here? What choose what? 150 choose 10. See, it's nice and simple. So we write this as there are 150 choose 10 possibilities. We can do a bit of simplification here. There's 150 factorial over 10 factorial times by, let's put it as 140 factorial. So it's 150 minus 10 factorial. We could write this out if we want to, 150 times 149 times by down to 141 times by 140 factorial over 10 factorial times by 140 factorial. You can cancel those. This is still a huge number. Okay, did anyone actually calculate it? Yep. So this roughly works out at 1.17 times 10 to the 15. That's obviously a ridiculously huge number. If this was an exam question, for example, I might ask to see this cancellation here. I might not, but if I ask to see cancellation, I'll simplify it first or leave it in calculator ready form. I would probably want to see it like this. If I ask to see an exact answer, or at least an approximate answer using your calculator, then this form here is fine. One thing to note here about factorials is factorials are kind of hard for us to grasp because things get really big really quickly, like completely out of our conception as to how big they are. Like if you see written down 99 factorial and 100 factorial, I don't know if your brain works like mine. I see these things and I think, well, 99 is close to 100, so these things are pretty close, right? But 100 factorial is 100 times bigger, right? 101 factorial is 101 times bigger than 100 factorial. So these numbers get huge really quickly. As soon as you start thinking about combinations of things quickly run away. Yeah,
So on a test, are we allowed a calculator?
that's a good question. I'll tell you when I've written the test. This is the kind of thing that, yeah, I might ask you for a calculator, but equally, I value more that you know how to write down this bit correctly than you knowing how to type these numbers into a calculator. So I might just ask you to leave it in calculator ready form. I'll see when it comes to it. Depends on the nature of the questions and how evil I'm feeling. Okay. How are you guys finding these questions? Are they good, easy? Good. Okay, I see some thumbs up. Good. Like I said, these are kind of nice because you can address lots of different types of questions. They're not too long. Okay, so now we're going to have an urn containing 6 green and 4 blue balls. You take out, so piece of information, 6 green, 4 blue balls. You take out 3 balls at random without replacement. It's that repetition there. We're not putting those balls back in, otherwise that would change things. How many different selections contain exactly 2 green balls and 1 blue ball? We're assuming that the balls are distinguishable. Okay. So what does this all mean? Let's think about what this looks like. So we've got an urn. I think this is a historic reason as to why mathematicians talk about urns rather than jars for now. We have 4 blue balls, 6 green balls even. And then what we're doing, we are taking out of this, we want to have a set of, what are we told? Exactly 2 green balls and 1 blue ball. So this is the set that we're creating. If it helps when you have something like this, draw a diagram. You know, it helps visualize what's going on. So what do we have here for these green balls? Well, there are 6 green balls in this urn. We're assuming that they're distinguishable. So there are 6 choose 2 ways to get them. Okay, so we're choosing 2 out of this 6. We only care about the combination. We care about the combination. We don't care about the order of these things. Okay. It helps you can think as well about these being numbered 1, 2, 3, 4, 5, 6. Likewise, we have balls 1, 2, 3, and 4 are blue. And suppose I'm choosing balls 3 and 5. We're told that they're distinguishable, so they're green, but they say have numbers on them, just like lotto balls. So we could choose 3, 4, we could choose 1, 2, and so on. There are 6 choose 2 ways of doing that. We have 6 objects, we're choosing 2 of them. 6 choose 2 ways. How about for the blue ball? Well, you want 1 blue ball, and there are 4 blue balls in there. How do we work this out? Or choose 1, yeah, which is just 4. So what does that mean? Well, this is the point where we use our multiplication principle. So there are 6 choose 2 times by 4 choose 1 possible selections. So what does that look like? We can do a bit of cancellation here because the numbers are quite low. So we've got 6 factorial over 2 factorial times by 6 minus 2 factorial. So that's my 6 choose 2. We have a 4 factorial over 1 factorial times by 4 minus 1 factorial. So we have 6 factorial times by 4 factorial over 2 factorial, which I'm just going to write as 2, times by 4 factorial times by 3 factorial. So 1 factorial is just 1, 2 factorial is just 2. These 4 factorials can cancel. What else can we do? could write out this 6 times by 5 times by 4 times by 3 factorial over 2 times by 3 factorial. So these 3 factorials cancel. We can also cancel this 2 with a 4 in the top. So that 4 becomes a 2. So we're going to have 6 times by 5 times by 2. Hopefully you don't need a calculator for. It's 60. So although you can just plug these things into a calculator, at this stage here, it looks kind of messy and complicated, right? But we can just expand these things out, do a little bit of cancellation, and we end up getting something that we can work out in our heads. Okay, I want you guys to have a go at this one. I will walk around and answer any questions you have. Pay careful attention to the wording of this question. Okay. Exactly. So I said you need to think about this one carefully. Okay, let's see how you guys got on. Who needs a little bit more time? Anyone? Okay, so this is a slightly evil question in the sense that we've been talking all about combinations, but I don't want you to forget about multiplication principle or about permutations. Okay, that's why I said be careful reading the question. Okay, so let's go through this. Suppose that a license plate consists of 3 letters followed by 3 digits. How many license plates can there be? So what are the total number of cards that we could register with these different license plates? If we can have repetition of letters, that repetition is key, but not of digits. Okay, so what does that mean for our letters? We can have repetition of letters. So what I like to do in these kinds of cases where I can draw them out is draw out what it looks like. Okay, so how many options are for the first letter? Well, there are 26 options here. We can have repetition, so we can have 26 here, and we can have 26 here. Okay, so we don't care about permutations, we don't care about combinations here. If this was a question of permutations and that you couldn't have a repeated letter, then we would have 26, 25, 24. Okay, so we'd have to, if you couldn't have A, for example, you couldn't repeat one of the letters, then you'd have 26, 25, 24. If for some reason you lived in a weird place where ABC and CBA were the same license plate, then you would have to think about combinations. That'd be a very weird place to live. Okay, if it just mattered what the collection of letters were, then you'd be thinking about combinations. Here, we're told that we can have repetition of letters. We can't have repetition of digits though. So here, how many possibilities are for the first number? Second? Third? I feel like I want to get you guys can carry on down to 0. So now we care about the ordering. We care about the ordering, obviously, but we also care about the repetitions. So that's why we've gone 10, 9, 8. So how many are there in total? We just multiply all these things together. So we can have 26 to the power of 3 times by 10 times by 9 times by 8, whatever that actually works out to be. Okay. So this was, like I said, slightly evil question because we've been talking about combinations. I want to make sure you guys don't forget that we can still think about permutations and we can think about multiplication principle as well. Okay. See how much time we've got left.
Yes.
I think we should be able to get through both of these. Okay. We've now got a standard deck of cards. We've got 52 cards arranged in 4 suits with 13 different values in that deck of cards. And we're going to think about combinations of hands that we can have in a game of poker. So in a game of poker, a hand consists of 5 cards drawn at random from the deck without replacement. How many hands are possible? Now, a key thing in poker is that the order of the cards, although it affects the betting, the order of the cards doesn't affect the final outcome in terms of what you have. So if you have, for example, 5 cards, 2, 3, 4, 5, 6, this is the same hand as having 3, 4, 6, 2, 5, right? These are counted as the same hand. The order of these things doesn't matter for the final hand. Therefore, here we care about combinations. We don't care about permutations. So how many hands are possible? There are 52 cards, and I'm drawing 5 from them. So it's just 52, choose 5. Again, a huge number. You can think about how unlikely it is to actually draw any set of cards. So counting is obviously intrinsically linked to probability. If we have a certain number of ways of doing something, if there's a fair way of doing each of those, then our probability of doing any of them is just going to be 1 over whatever the total number of outcomes are. Okay, so probability and counting are very closely linked. Okay, part B is a little bit more complicated. Right, so how many hands consist of exactly 1 pair? So that's 2 cards of equal value, with the 3 other cards having different values. Okay, so what does this look like? So suppose if you're playing Texas Hold'em, you get given 2 cards initially. So we want these to be a pair. And these things here to have 3 different values and different to what you start with as well. For example, you could have 2 aces and then Jack, Queen, King. That would be the type of hand, sorry.
That's a good guess.
Kind of. I mean,
Depends on what the cards that are looked at.
well, if these are, oh, I guess, yeah, you still need to have the turn and the river, right? We're not gonna think about the other 2 cards in Texas Hold'em, actually. I can't remember what variation this would be called if you just have the 3 cards rather than the turn and river. Any poker experts here? Then is this, what's this version called, where you just have 3 down on the table of no turn or river?
Oh, so
This is going to be on the test. It's not going to be on the test, so I'll get quoted for that. Okay, so how many ways are there to do this? Okay, the first thing we need to do is we need to choose a pair. So we need to choose, how do we choose a pair? Well, there are 13 different values. So the first card in that pair, there are 13 choose 1 ways of doing that, which is just going to be 13. It's just the first card that you're dealt. You need to have this being a pair. So you need to have this multiplied by the number of suits. There are different, obviously we can have, say, ace of hearts, and we can have ace of spades, and so on. There are also ace of diamonds and ace of clubs. We want 2 of these. This is just for aces, but we're going to replicate that for every single value there is. So that's where the values come in here, whether you're ace, 2, 3, and so on. And then the suits come in the second part here. So here we've got 4 suits. We're choosing a pair, so it's 4, choose 2. Okay, so that deals with this pair. Let's color code these. So that deals with that part. We're then asked to draw 3 more that have different values, so different to each other and different to the pair. So in this case, well, we need different values to the pair. We've already taken 1 value out, so that only leaves 12 possible values that it can be. So if I've got ace of hearts and ace of spades, I want the next thing can't be an ace because it will match that, okay? We want these 3 cards, I'll code it differently, these 3 cards in pink all have different values to each other and to the initial pair. So we distinguish from the initial pair with the 12. And we're choosing 3 different values. There's going to be 12, choose 3. The final thing we need to account for is the suit of those cards. So for each of those 3 cards, there are 4 possible choices of suits. 4 choose 1, 4 choose 1, 4 choose 1. So this pink bit deals with the 3 cards of different values. The orange bit deals with the pair that we start with. We can write this a little bit simpler. So 13 choose 1 is 13. I'm going to leave it as 4 choose 2 and 12 choose 3. We could cancel those as well. The 4 choose 1, 4 choose 1 is just 4. N choose 1 is always just n. So here we're going to have 4 cubed on the end. Again, you could plug this into a calculator if you wanted to. Okay. Let's go through one more problem together. This one I think is quite profound. So suppose that DNA is decoded into protein, that when a DNA is decoded into protein, the letters CGAC of the DNA sequence are read in ordered groups of length K. Okay, for example, if K is equal to 4, then this sequence here, we would split it up into AGTA, then CTAG, then ACCG. Okay, so we have a string of letters in our sequence, and these are read in groups of K. And suppose that each group of K letters codes for a different amino acid. And each letter can be G, T, C, or A. If there are 20 amino acids, what is the smallest value of K that allows coding for them all? So what's this trying to say? It's saying, okay, we have a sequence like this one that we're given in the question, a sequence of letters. When this is read, we could read it in blocks of 1 or 2 or 3 or 4, and these are non-overlapping blocks. We need to be able to code for 20 amino acids. How can we do that? In other words, what we're asking here is we're asking how many words, and words in the loose sense here are just different combinations of G, T, C, and A. How many words are there of length K in the alphabet of G, T, C, and A? So here, our alphabet only contains 4 letters. What we're asking then is we want there to be 4K words, 4 to the power of K words. Why to the power of K? Well, we have 4 letters, and we're choosing K of them in each of these combinations. So if K is 1, our possible words are G, T, C, and A. If K is 2, then we can have G, T, G, C, G, A, and G, G, and then all the others as well. So we end up with 4 to the power of K words. What do we want? Well, we want this 4 to the K to be greater than or equal to 20. Why 20? Well, because we were trying to code for 20 amino acids. So let's just think what these different values of K give us. 4 to the 1 is just 4. 4 squared is 16. 4 cubed is 64. So having words, genetic words of length 2 is only going to be able to code for 16 amino acids, but we need 20 amino acids. So words of length 2 are insufficient. Words of length 3 are sufficient. So K equals 3 is the minimum. And this is actually what happens, right? If you have a sequence like this one above here, I go back to it, this is read in blocks of 3. Really interesting thing in terms, I don't know what you guys know about the history of cracking the genetic code, but when people are trying to understand like how it encodes, how we go from these genetic sequences into proteins, how do we read these? The key thing that caught people out for a long time was this idea of degeneracy. So because you have these A, G, T, and C can be rearranged in 64 different ways in length, in words of length 3, that means that the same amino acid can be encoded by multiple different sequences. So for example, AGT could, in theory, be the same as CAT. These could give you the same amino acid. They probably don't, because I don't know what amino acid codings are. The point being that this was really fundamental to trying to crack the genetic code, this idea of degeneracy. And we can see a little bit of that with counting. Anyway, that's it for today. I will see you on Friday.